So imagine you had three charges sitting next to each other, but they're fixed in place. So somehow these charges are bolted down or secured in place. We're not going to let them move. But we do know the values of the charges. We've got a positive 1 microcoulomb charge, a positive 5 microcoulomb charge, and a negative 2 microcoulomb charge. So a question that's often asked when you have this type of scenario is, if we know the distances between the charges, what's the total electric potential at some point? And let's choose this corner, this empty corner up here, this point P. So we want to know what's the electric potential at point P. Since we know where every charge is that's going to be creating an electric potential at P, we can just use the formula for the electric potential created by a charge. And that formula is V equals K, the electric constant, times Q, the charge creating the electric potential, divided by R, which is the distance from the charge to the point where it's creating the electric potential. So notice we've got three charges here all creating electric potential at point P. So what we're really finding is the total electric potential at point P. And to do that, we can just find the electric potential that each charge creates at point P and then add them up. So in other words, this positive 1 microcoulomb charge is going to create an electric potential value at point P, and we can use this formula to find what that value is. So we get the electric potential from the positive 1 microcoulomb charge. It's going to equal K, which is always 9 times 10 to the 9th, times the charge creating the electric potential, which in this case is positive 1 microcoulombs. Micro means 10 to the negative 6th. And the distance between this charge and the point we're considering to find the electric potential is going to be 4 meters. So from here to there, we're shown is 4 meters. And we get a value of 2,250 joules per coulomb is the unit for electric potential. But this is just the electric potential created at point P by this positive 1 microcoulomb charge. All the rest of these charges are also going to create electric potential at point P. So if we want the total electric potential, we're going to have to find the contribution from all these other charges at point P as well. So the electric potential from the positive 5 microcoulomb charge is going to also be 9 times 10 to the 9th, but this time times the charge creating it would be the 5 microcoulombs. And again, micro is 10 to the negative 6th. And now you got to be careful. I'm not going to use 3 meters or 4 meters for the distance in this formula. I've got to use distance from the charge to the point where it's creating the electric potential. And that's going to be this distance right here. What is that going to be? Well, if you imagine this triangle, you've got a 4 on this side. You'd have a 3 on this side, since this side is 3. To find the length of this side, you can just do 3 squared plus 4 squared, take a square root, which is just the Pythagorean theorem. And that's going to be 9 plus 16 is 25, and the square root of 25 is just 5. So this is 5 meters from this charge to this point P. So we'll plug in 5 meters here. And if we plug this into the calculator, we get 9,000 joules per coulomb. So we've got one more charge to go. This negative 2 microcoulombs is also going to create its own electric potential at point P. So the electric potential created by the negative 2 microcoulomb charge will again be 9 times 10 to the 9th. This time times negative 2 microcoulombs. Again, it's micro, so 10 to the negative 6th. But notice we are plugging in the negative sign. Negative charges create negative electric potentials at points in space around them. Just like positive charges create positive electric potential values at points in space around them. So you've got to include this negative. That's the bad news. You got to remember to include the negative. The good news is these aren't vectors. Notice these are not going to be vector quantities of electric potential. Electric potential is not a vector quantity. It's a scalar, so there's no direction. So I'm not going to have to break this into components or worry about anything like that up here. These are all just numbers at this point in space, and to find the total, we are just going to add all these up to get the total electric potential. But they won't add up right if you don't include this negative sign, because the negative charges do create negative electric potentials. So what distance do we divide by? Is the distance between this charge and that point P, which we're shown over here as 3 meters, which if we solve gives us negative 6,000 joules per coulomb. So now we've got everything we need to find the total electric potential. Again, these are not vectors, so you can just literally add them all up to get the total electric potential. In other words, the total electric potential at point P will just be the values of all of the potentials created by each charge added up. So we'll have 2,250 joules per coulomb plus 9,000 joules per coulomb plus negative 6,000 joules per coulomb. And we could put a parenthesis around this so it doesn't look so awkward. So if you take 2,250 plus 9,000 minus 6,000, you get positive 5,250 joules per coulomb. So that's our answer. Recapping, to find the total electric potential at some point in space created by charges, you can use this formula to find the electric potential created by each charge at that point in space, and then add all the electric potential values you found together to get the total electric potential at that point in space.